Greetings, math friends. I want to use the chain rule to take the derivative of this function. So I have this chain rule written here in Leibniz notation. I want to look at the individual derivatives here, that the product of these will give me the derivative of this. To be able to take these individual derivatives, I'm going to look at this as a composite function, and I'm going to decompose it into the functions that make up this composition. I want to recognize that if I take this piece out of what I'm square rooting, then this will stand alone as a function. So we could say that y is the function, the cube root of v. And the function v can be 2 plus this. I'm going to take the e to the x out as its own function. So this is going to be 2 plus u. And then I'm going to say that u is e to the x. So I have these three functions. If I compose them together, then I have this. This would go inside of here. This would go inside of here, which is going to be inside of here, giving me this. So now I'm going to be able to look at the individual derivatives here. I can take the derivative of y with respect to v, the derivative of v with respect to u, and the derivative of u with respect to x. So that's what we're going to do. So when we take this derivative, we get 1/3 v to the negative 2/3 power. Over here, we are just going to get 1. The derivative of 2 is 0. The derivative of u is going to be 1. And then the derivative of e to the x is just e to the x. All right. Now that we have these individual derivatives, according to the chain rule, we are going to multiply those together. So that's exactly what we're going to do here. So I'm saying by this theorem, dy dx is going to be the product of these things. All right. The u's dropped out because the derivative was 1, and that's the multiplicative identity, so it doesn't change the magnitude of this. We have one thing that we need to do here. We want everything in terms of x, and we have this v in here. So to get it back in terms of x, we have to do some substitutions. The first thing that I'm going to substitute in is I'm going to go up here and look at v, and see that v is 2 plus u. So I'm going to substitute that in for v. Now that I have that substitution, I still don't have everything in terms of x because I have u here. I can look back here and see that I have u is e to the x, so I can substitute that into there. So now I have everything in terms of x. So the derivative of the original function that I have here is going to be this. 1/3 times 2 plus e to the x to the negative 2/3 power times e to the x. Now, this you can rearrange algebraically and get another form. We can rewrite this this piece here algebraically so that it's this here where we have this fraction with e to the x in the numerator. We have 3 times the cube root of 2 plus e to the x squared. So algebraically, these are equivalent, and there are some intermediate steps there. If this should be a problem that you see in your textbook, you may have come up with this, and then you look in the back of the textbook and they have something like this. You need to recognize that they are algebraically equivalent. You did get the right solution. If you have an instructor that has some kind of expectation of this rational form versus this form here, you would want to make those adjustments according to the expectations for the class that you're in. Hopefully this has been beneficial to understanding how this chain rule statement actually applies to a function like this, where we have a composite function, and how to break that down so that we can get these individual derivatives. Cheerful calculations.